Hi everyone, this is the first video for section 2.1, and so chapter 2 is all about sets, and this section is all about sets as well. Okay, so at this point, again, just make sure you've gone back and read section 2.1 in the books because, well, this section is mostly definitions. But yeah, make sure that you understand these definitions. We're going to go over them again. And just so that you understand what all of these things are and that you remember what all of these things are, I would definitely recommend making flashcards either on Quizlet or physical flashcards of all of these definitions because, as you can see, this is mostly definitions. But we're just going to go through them. Okay, so a set is actually kind of an abstract thing. It's a collection of things. It doesn't have to be even mathematical things. You could just have a set of cows, a set of pigs, a set of cars, and it's just a collection of objects, right? They don't have to be anything special or fancy. Yeah, it's just a set of things. And so whenever we have, so a lot of times these are going to be sets of numbers. For everything that we actually do, we will have sets of different types of numbers. So we're going to have sets of whole numbers, sets of counting numbers, sets of integers, rational numbers, real numbers, and so on. And so we're just kind of going to go through what are sets in general so that later on we can talk about these specific sets of numbers. So like I said, a set is just a collection of objects. And so when an object is in a set, it's called a member or an element of the set. So a lot of times I'll say element. That's what I tend to use just because of this notation. So we write that an object is an element of a set by this E here. So we write this as X is in E. So let me write this. So you can write this just kind of a big C and then put a line through it. And that's how you write that. This is an element of the big set X. So I will say, make sure when you're writing any of these things that it's easy to distinguish between the little x and the big X. I understand that it's really hard to do that, but just have some way to distinguish between those things. Yeah, so if something is in a set, if it's an element of the set, we write that X is in the little set. Little x is in the big set X. So normally we will denote sets by the capital letters, so this big X, and we'll denote elements by lowercase letters, by the little x. So if it's in a set, we have X as an element of the set, and if it's not, we have it's not an element of the set, right? So just down here, so we have the element and draw a line through it, just like exactly how we do not equal to. So it's not an element of the set X. Okay, so we have a set, and we can have things in this set that are called elements. And so now I want to kind of compare them. So I'm going to have kind of a motivating example to go through this. I know that there's examples in the books, but I'm just going to have a motivating example as we go through these. So that's just going to be the set here, A. Okay, so we have our set A, and it has all of these things in it, right? It's gonna, everything in that circle is going to be in the set A. So we have this concept of a subset that's a set that's some part of some other set. So representing that with this picture, we can have this other little circle, C, that is a subset of A, right? Because everything that's in C, right, every member that's in C is also a member of A, right? Because everything in C, in the C bubble, is clearly already in the A bubble, right? So that's what all it means to be a subset. It's everything in one is also in the other, right? So thinking about this in our conditional form, if an element is in C, then it is in A, okay? So let's go ahead and give these sets some names, right? We can just deal with A and C abstractly, but let's look at the set of animals. And let me zoom in a little bit here to write the set of cats. So we have the set of cats, and it's inside the set of animals, right? Because we know that every cat is an animal. Okay, so then we have this concept of a proper subset, which means that we have a subset that's not equal. So we can see the difference in the notation here. It has the equal sign at the bottom, and this one here does not have the equal sign at the bottom. So those are distinguishing things, right? If it doesn't have the equal sign, that means that X cannot be equal to Y, right? The two sets cannot be equal. So this right here, this animals and this cat set, are examples of a proper subset. Because yes, every cat is an animal, but not every animal is a cat. So this is really similar to, right, the concept of every square is a rectangle, but not every rectangle is a square. So it's really similar to that. We have this proper subset. So this notation probably isn't familiar to you, but it's really similar to thinking about the less than or equal and the less than symbols, right? So we can have 3 be less than or equal to 4, or just 3 is strictly less than 4, right? And if 3 is strictly less than 4, that means it can't be equal to. And it's the exact same thing with these subsets. Just think about it in the exact same way. That 3 is to the left of 4 on the number line means that 3 is less than 4. It's a similar concept. Okay, so we can describe sets in a lot of different ways. So we can use words. So for this one, we're going to look at the set of even numbers. So we'll say that X is the set of even numbers. Okay, so we can just say what it is in words, or if we're a little bit unsure of what that looks like just by the description in words, we can make a list where X is this set that we're about to write. So whenever we list out the elements in a set, we're going to use these curly brackets. So curly brackets look like this. You can see them on your computer and your phone if you go and look at it. But yeah, we're going to use these curly brackets so we can just list out the elements, right? Even numbers 2, 4, 6, 8, 10, and we can use these ellipses to just say, and so on, right? There's a ton of even numbers, right? We can just keep going on forever. And then we close it with another curly bracket. So one thing to note on these curly brackets, so mostly on exams where you write out your answers, so we're always going to use curly brackets. So practice writing these if you struggle with it. Definitely for any exam, I just need to be able to read what you're writing. Just like whenever you're teaching and you're grading your students' work, you want to be able to see what they're writing. So we're going to use curly brackets. We're not going to use parentheses, and we're not going to use double-sided 3s and backwards 3s, okay? You can use curly brackets, or if it's really hard, you can just use squiggles. That's good enough. There's nothing else that could mean besides these brackets. So just be careful whenever you're writing these to make sure that I can understand what you're saying. Okay, so next, the third way that we can describe a set is to use set builder notation. So set builder notation, again, always has these curly brackets, and it's this X, right, little x that's in the set, and then there's this vertical line. So this vertical line right here is said verbally as such that. So this set contains X such that X has whatever property we're looking for. So this one is going to be X such that X is even. Okay, so that's our property. So that's our set builder notation, where we have this vertical line that after the vertical line, we put the property that all of these things need to have to be elements of the set we're talking about. So these are the 3 different ways that we can describe the set. So like I mentioned at the beginning of this video, there are specific sets that are going to be more important for us throughout this class. So they're mostly going to be types of numbers, sets of numbers, right? Because this is a math class and we're going to deal with different numbers. So the first set of numbers that we even learn, right, in school as kids is the set of natural numbers. So this is also called the counting numbers. This is also called the counting numbers, right? It's the natural numbers. It's the numbers we can hold up on our hand, right? 1, 2, 3, 4. You can hold it up on your hand and visualize it. So this is denoted by this little, you write this down. We typically write it as this little double line and then finish writing the end. The next one that we do, whole numbers. So really you can see that the only difference here in this list notation between the whole numbers and the natural numbers is the presence of 0. So 0 is a whole number, but it's not a natural number, right? So a way that you can think of to remember which one is which, so you can think of natural numbers as the one that you can hold up on your hand, right? It's harder to represent 0 on your hand. I know you can hold up no fingers, but it's harder to know what's going on then. But the whole numbers include 0. And so that's just represented by a W, sometimes a little bolded W, right? So the bolded is normally, you can see on the left side. The next one is the integers. So this one takes the whole numbers and we include the positive and the negative. And so, yeah, the integers are just the whole numbers, but we take the positive and negative versions. So this is, right, your traditional number line that goes on both sides of 0. So this one is written where you can write it like a little 7, and then you go back and do the opposite way. Let me write that a little bit better. We go back and write it the opposite way for Z. The next one is Q, the rational numbers, which is, right, this one, we wrote it out in words. It's all the numbers that can be represented as the ratio, which ratio should make you think fraction, of 2 integers as long as the denominator is not 0. So this one is written out in words, and we're going to try and write it in set builder notation. So we just take these words and make them in set builder notation. So we have that Q, this is the way you write Q, is you make a Q, and then to bold it, you put just a little line right here. So this is going to be the set of ratios or fractions of 2 integers that we can represent by A and B. And then we have the such that, and we have that A and B need to be integers. So A and B need to be elements of the set of integers. And we need the denominator, right, the B, to not be equal to 0. So don't be overwhelmed if this didn't seem as natural to you, right? Once you practice with this and see how to write different sets in set builder notation, it'll be more clear of how to take these words. All numbers can be represented as the ratio of 2 integers with the denominator not 0 and put it in the set builder notation. Okay, so this is, the rational numbers are essentially just the fractions, right? That's all this rational coming from ratio, which just means fractions. So the only other set of numbers that isn't explicitly listed here are the real numbers. So this one, well, I'll do it again. You, again, bold on the left-hand side, and then finish your R. So this is the real numbers. Okay, so these are pretty much the sets of numbers that you're going to need to know and be comfortable with. The natural numbers, the whole numbers, which just adds 0, the integers that adds the negatives, the rational numbers that puts it into fractions, and then the real numbers, which is kind of everything else, right? It's everything else that we typically deal with. Okay, so now we're going to look at, well, before we move on to properties of sets, I want to also mention another important set that's not of numbers, but that doesn't have anything at all. So we also have this concept of the empty set that looks like this 0 with a slash through it, and that slash should extend past the 0, right? It should be a slanted slash. So this is the empty set. And so this empty set, oh, it's actually talked about later. I'm sorry. I'll just erase that and we will keep going on. Okay, so once we have some examples of sets, we can talk about certain properties of sets. So this set, a set can have a cardinality, which just is the number of elements in that set. So how many things are in there? So for example, if we have that X is the set of natural numbers, so we take things that are natural that are less than or equal to 3. Right, we want to look at natural numbers that are less than or equal to 3. Well, this, if we list it out, is just the same thing. So this is natural numbers, so we start at 1, and then we include 2, and then it's less than or equal to 3, so we include 3. So it's just counting how many things are in a set, right? This set, the cardinality of it is 3, because there's 1, 2, 3 elements in the set. So we just have that cardinality of the set, counting the number of things in it. So if the number of elements is a whole number, then it's finite, right? This one has a whole number, 3 sets, but we can also have sets with an unlimited number of elements. And this is kind of all of the sets we talked about above, right? These special sets, the natural numbers, well, it's 1, 2, 3, 4, 5, 6, 7. We can go on counting forever, right? We can keep counting up. I mean, even as kids, we got so proud of how high we could count, but you can really keep counting forever. So there's an unlimited number of things that you can count. And then because all of the other sets, in the whole numbers, we add 0, the integers, we add the negatives, the rationals, we put it in fractions, these just keep getting bigger. So these are all infinite sets that we talked about up here. Okay, so now back to that special set. So we use empty set to mean the set with no elements. So for example, if we took the number of natural numbers that were strictly less than 1, well, all of the natural numbers are 1 or bigger. So that has nothing in it. It's just the empty set. So like I said earlier, the empty set is 0 with the slash through it. We want the slash to actually be diagonal and to extend past the 0. So it's called the empty set or the null set. Null meaning there's nothing in there. Null meaning nothing. Okay. And then lastly, a well-defined set is a set where there's no question about whether an element is in there or not. So an example of a set that's not well-defined is this, where X, well, let me write it in a list. Well, not a list, words. Where X is the set of tall people. So this isn't well defined because what is tall? So similar to how last time, or in chapter 1, we had that the figure is pretty isn't a statement because it's subjective. It's the same reason that this is not a well-defined set, because this property of being tall is subjective, right? It's not easily measurable because tall means different things to different people, right? This would be a well-defined set if instead it was X is the set of people who have height taller than 6 feet. That would be a well-defined set because you can objectively measure, does someone meet this qualification? Okay, then that is in this set or not. Okay, so next time we're going to talk a little bit more about subsets, and for now, that is all for this video.